Let's jump right in. Welcome to this explainer. If you're staring at a mountain of chemistry notes right now and feeling completely overwhelmed, take a deep breath. You've got this. Consider this your exclusive one-on-one tutoring session. Today, we're going to absolutely demystify the Cambridge O-level chemistry syllabus and hack this exam together. We're looking at the exact frameworks, the hidden patterns, and the essential checklists you need to turn all that confusion into total confidence. Here's our daily study blueprint. We're breaking that massive textbook down into 5 highly manageable modules: kinetic theory and matter, conquering moles and equations, periodic table exam trends, lab safety and practicals, and finally, alternative to practical strategies. This is the exact structure designed to guarantee you maximum marks. Let's get into it. Starting things off with Module 1, kinetic theory and matter. Before you can balance a complex equation, we've got to build the foundation of how the physical universe actually behaves. To really get chemistry, you have to connect it to the real world. Think about dramatic geysers erupting with steam, or, just your car windows misting up on a freezing cold morning. These aren't just random things happening. They're actually visible, real-world proof of the kinetic particle theory in action. What you're literally seeing is particles gaining or losing heat energy, speeding up or slowing down, and ultimately breaking or forming their attractive bonds to change state. It's pretty cool when you think about it.
And what's really important is how directly these concepts translate into exam points. When an examiner asks you to compare states of matter, you need to use precise vocabulary to secure those marks. Emphasize that solid particles vibrate in fixed, tight positions with a regular structure. That's exactly why solids expand when heated but just cannot be compressed. Contrast that directly with gas particles. They've completely broken their attractive forces and they're just moving randomly at really high velocities in all available space.
Now, this brilliantly illustrates diffusion, but specifically in liquids. We usually just think of gases spreading quickly across a room, right? But check out this green food coloring in water. Because liquid particles move so much slower than gases and just have way less energy, the color actually takes days to fully mix and reach that completely uniform state you see on the right. Let's put this into practice with a classic exam-style question. Why does butter soften on the counter, but the smell of coffee reaches you instantly? Think exactly like an examiner here. Use kinetic theory. You'd explain that the coffee gas particles have a very low mass and a high velocity, so they diffuse super rapidly across the room. But the butter solids, they're just gaining enough heat energy from the room for their particles to slightly overcome those attractive forces and slide past one another. That's what turns it from a hard solid into that softer, semi-liquid state. Moving right along to Module 2, conquering moles and equations. This math is the biggest hurdle where students usually drop marks, but I promise you, it's really just a set of rules. The absolute best piece of advice I can give you here is don't let massive blocks of text in a word problem freak you out. Just offload the math by following 3 foolproof steps every single time you hit a mass calculation. Step 1, write down your balanced equation. Step 2, convert your given masses into moles. And step 3, compare the molar ratio to see which reactant runs out first. Boom, that is your limiting reactant. So let's actually apply those steps to an exam question. What mass of hydrogen gas is produced if 46 grams of sodium completely reacts with water? Okay, step 1, write the balanced equation for sodium and water. Next, grab your periodic table and look up the relative atomic mass of sodium. It's 23. Now, convert your 46 grams into moles simply by dividing 46 by 23. That gives you exactly 2 moles of sodium. Then just look at your balanced equation to find your proportional hydrogen output. And just like that, you've completely unlocked the answer without any of the panic. Welcome to Module 3, Periodic Table Exam Trends. This is where we stop blindly memorizing facts and start actually decoding the hidden patterns of the elements. You are definitely going to see questions contrasting elements on your papers. Look at the stark differences presented here between a group 1 alkali metal, like sodium, and a transition element, like copper. Notice how sodium is soft, highly reactive, has a low density, and only has a single +1 oxidation state? Copper is the complete opposite. It's hard, less reactive, incredibly dense, and boasts variable oxidation states. Contrasting these properties is a massive, high-yield exam topic. As a senior examiner, here is my absolute best secret tip. Treat the periodic table like a predictive cheat sheet. Please don't try to memorize every single element. Instead, learn to predict how elements will react based purely on their atomic structure. For instance, metallic character increases as you move down a group. Why? Because those outer shell electrons are getting further away from the nucleus, making them so much easier to lose. It's all about recognizing that trend. Let's pivot to Module 4, Lab Safety and Practicals. This is totally crucial because your lab skills directly translate to exam points, even on the written test. Before you even think about grabbing a test tube in your practicals or outlining an experiment in your written answers, examiners are actively looking to see if you've considered safety protocols. Showing them that you know to use a fume cupboard for toxic gases like chlorine, or that you always conduct a risk assessment for known hazards before starting, that immediately signals to them that you are a competent, top-tier chemistry student. Now, here is a spot where so many students literally throw points away. Before you plan any investigation, you absolutely must identify your variables. If you're testing how temperature affects the rate of a reaction, temperature is your independent variable. It's the thing you were changing. The volume of gas collected, that's your dependent variable, the thing you're measuring. Nail this down first, and the rest of your experimental design will just fall perfectly into place.
And finally, Module 5, Alternative to Practical Strategies. This paper tests your lab skills on paper, so your data analysis has to be razor sharp.
You really have to know how to confidently interpret experimental findings from a scientific table, like this one right here, tracking oxygen collection over time. You should be able to look at this data, instantly recognize the rate of reaction slowing down as that volume levels off, and then confidently plot it onto a graph, making sure your axes are precise and correctly labeled. A really good chemist, and definitely a top-scoring student, is constantly evaluating their data. When you plot that graph, if you spot a sudden drop or an unexpected spike in gas volume that just does not fit your curve of best fit, well, you found an anomaly. Your job is to circle that anomalous result and explain exactly why it happened. Was there a gas leak in the syringe? A sudden drop in room temperature? Identifying those experimental errors is just as important as getting the correct result. When it comes to those intimidating, long-form, written answers, structuring your response sequentially is how you guarantee maximum points. Please don't just write a messy wall of text. First, state the aim or the exact chemical rule you're applying. Second, clearly display your math on distinct lines and always include your units. Finally, compare your initial expectations against your actual analytical conclusion. Just make it incredibly easy for the examiner to give you the points. We have covered a massive amount of ground today. I'd highly recommend taking a screenshot of this complete revision checklist right now. If you can confidently tick off these 5 pillars, kinetic theory, mole calculations, periodic trends, lab safety, and data interpretation, you've successfully absorbed this entire study guide. You really have the foundational tools to tackle almost anything the syllabus is going to throw at you. So, I'll leave you with this. Chemistry is no longer a foreign language. It is just a set of rules waiting to be applied. You've got the examiner's playbook now. You know the patterns, you know the structures, and you know exactly how to avoid those common pitfalls. The only question left is, how are you going to use these chemical patterns to completely decode your final exam? Get out there, trust your preparation, and go claim those marks. Keep exploring, keep questioning, and I'll catch you in the next explainer.